Welcome back. In this video, we're going to build what we learned on Lewis structures in the previous video and see how we can take this shape that we've shown, right, the connectivity of the atoms through the Lewis structure, and then conclude about what the actual shape of that molecule will be. Because we'll see that there's going to be slightly more to this phenomenon, this molecular geometry, than just the number of bonds that a certain central atom is making. That is to say, just because we have two atoms that one atom is connected to, doesn't mean that it's always going to have the same shape. And we'll learn the factors that determine the different possible shapes in this following video. Because what we'll see is the shape that a molecule actually takes, whether it's a straight line or whether it's bent or whether it's a triangle, that is going to determine what we call the polarity of this molecule. And that is to say whether or not the molecule can act almost as if it's a permanent little magnet and therefore have interactions with other molecules nearby. Because this polarity is going to determine many properties of these molecules that we'll see in the upcoming video as well. And so understanding very clearly the shape of these molecules we'll see has just a really tremendous effect on the molecule's properties and is just very important to understand well and is rather interesting when you think about the different molecules that you know already and that they have unique shapes that all instances of that molecule will take up. All right, so now we're going to be talking about molecular geometry. We should be pretty comfortable with predicting the Lewis structures for these covalent molecules. And now what we're going to see is how we can connect those Lewis structures, which show how the different atoms are connected, into the actual shape of molecules, because we do know that they exist in a 3D world, and their geometries are going to reflect that as well. And the main theory that we're going to be using here is called the Vesper theory, valence shell electron pair repulsion. And this says that when we have electrons around a central atom, right? So if there's an atom in the middle, that's the one around which we're going to have geometry, not the hydrogen at the end, because it's kind of just capping off the end and doesn't really have any geometry. But these central atoms are going to have shapes based on the idea that negative charges will repel. And recall the electrons are where the negative charge exists on an atom. And whether we have a covalent bond or a lone pair of electrons, these are, in both cases, negative charges that are going to want to repel, right? Whether we're bonding or non-bonding, right, meaning a bond or a lone pair, we're going to repel one another in order to take up positions to maximize the space that those bonding or non-bonding electrons have around the central atom. And so let's consider our sort of quintessential example. This is methane Ch4, and it has this specific shape shown below, where the angle is going to be 109.5 degrees around the central atom. And how do we get that? Well, this is the shape that the different bonding domains, there are only bonding domains here, right? 4 bonds, no lone pairs around the carbon. This is the shape that the methane molecule will take up in order to accommodate these 4 bonding domains and no non-bonding domains, right? We can kind of see that 2 of the hydrogen shown in the top right picture will be within the plane of the page, right? These are just the lines, right? It's sitting kind of right in the page. And then we have a dashed hydrogen that's kind of going backward, and a spear hydrogen, the solid triangle looking like bond, that's coming forward. And so what we see here is that when we are accommodating these the 3D space that this molecule wants to occupy, that the bond angle is 109.5 degrees. And this gives us what we'll know as the tetrahedral geometry. And if we were to connect all of these hydrogens, it would sit kind of like a triangular prism, right, with equilateral triangles on each side. So keep in mind, right, that each domain wants to occupy as much space as possible. And so when we have 4 domains, we're going to be based on this tetrahedral geometry, which we just saw with our methane molecule. If we only have 2 domains, such as the following molecules shown here, right, this HCN or the carbon dioxide, doesn't matter if they're single bonds or multiple bonds, right? 1 single bond and 1 triple bond means 2 bonding domains. 2 double bonds means 2 bonding domains. We'll have this linear geometry, right? If these 2 domains want to spread as much across from each other as possible, they'll do so by being directly across, right? 180 degrees. And if we have 3 domains, we have a trigonal planar geometry. Now, we're going to see that when we add in some lone pairs, things get just a tad bit more intricate. But these are the parent structures we want to keep in mind, right? Whether we have bonding or non-bonding electrons, right? in this case, we're only bonding electrons around the central atom, we're going to take up these parent structures, right? And we're going to see coming up what happens if we are to replace some of these bonding domains with lone pairs. So let's consider, right, H2O versus CO2, right? And so what we have here is carbon dioxide, which has 2 bonding domains, versus water, H2O, which actually has 2 bonding domains and 2 non-bonding domains. And you may see already that I've drawn these two slightly differently, right? These depictions show water differently than it does carbon dioxide, right? Carbon dioxide has this linear geometry, where water is showing something else. What is different? Well, the difference is in these lone pairs, and therefore, water is going to be based on a tetrahedral geometry because it actually has 4 electron domains, 2 bonding and 2 non-bonding. The difference, though, is that it's not actually going to be the tetrahedral shape that we looked at before because these electrons don't really have any mass compared to the hydrogens or the oxygens. You know, compared to 1 proton, an electron is just so much smaller that we count it as basically massless and dimensionless effectively as well. So they will definitely affect the shape, right? The existence of these lone pairs means that the water is going to want to be in a fundamentally tetrahedral geometry, but those lone pairs aren't really going to be part of the shape. It's really just going to be those 2 bonding pairs connecting the oxygen and the hydrogen that are forced away from that linear geometry. And so again, we'll call that parent geometry the electron geometry. And for CO2, that electron geometry is based on 2 zones, and we're therefore going to have a linear molecular geometry as well, because there are no lone pairs, right? Linear electron geometry based on that linear structure, and we're going to also have, of course, the linear, what we'll call molecular geometry. In other words, CO2 is a line. Water, on the other hand, is based on that tetrahedral electron geometry because it has 4 zones. However, 2 of those zones are lone pairs and don't actually contribute to the shape itself. They are only distorted by those electrons, the lone pair electrons. And therefore, what we'll have here is a bent molecular geometry where water is not linear like CO2, even though both have 2 bonding domains. The existence of those lone pairs forces the linear structure into a bent structure. So again, the existence of these lone pairs are very important. We're going to see that this shape affects physical properties of water. We know that the physical properties, right, are actually very different. CO2 is a gas at room temperature and water is a liquid. This shape is a lot to do with that, right? For now, though, keep in mind that the geometry is going to be determined both by the lone pairs and the bonded pairs, but that the lone pairs don't actually take up space. They just help determine the space. And we want to determine the parent structure based on all the electron domains, bonded and non-bonded. So here's a nice little chart that shows us, the different electron domains, right? Again, we want to consider both the bonded and the non-bonded. And what we have here is with 2 regions, we have a linear angle. With 3 regions, we have a trigonal planar with 120 degrees of separation. And we should be getting pretty used to this tetrahedral geometry by now. Again, we want to determine these parent structures based on both bonding and non-bonding electrons. And we're going to call this the electron geometry, and we're going to determine the molecular geometry based only on the bonded pairs, but keeping in mind that they may be affected by the lone pairs. If there so happens to be no lone pairs, like in the example of CO2 on the previous slide, the electron and molecular geometries are going to be equivalent. So here's another kind of good chart that shows for up to 4 bonding and non-bonding domains what the different shapes are for these different potential molecules, right? And if we look at the top row, right, if there's 2 electron regions, the only option is to have no lone pairs, and we have linear. In the second row, if we have 3 regions, we could potentially have all bonded, or one of those could be non-bonded, right? 1 lone pair and 2 bonded pairs. In which case, right, similar to the water example, that lone pair will force the bonded pairs away from that linear geometry and make it a bent or angular structure. In tetrahedral, right, that's our 109 degree spacing. When we replace one of those bonds with a lone pair, we end up having a trigonal pyramid, right, so just one of the top bond removed. And if we have 2 removed, we have that bent structure for water. One thing to keep in mind here is that when we have a lone pair, it's actually a little bit greedier for space compared to the bonded pairs. And so when we have the bent or angular with 3 regions, or the trigonal pyramid, or the bent or angular like water, the angle is actually going to shrink up just a little bit because of the existence of those lone pairs. So let's go ahead and take a look at this chart, or perhaps you're just kind of thinking of things. And what is the shape of a molecule with 3 bonds and 1 lone pair? Go ahead and pause the video and see if you can come up with the right one. All right, hopefully you were able to come up with an answer, and it is indeed C, the trigonal pyramid. 3 bonds, 1 lone pair, that is 4 total electron regions, one of which is a lone pair, and that gives us our trigonal pyramidal shape. Keep in mind that if we do have more than one central atom, such as in the following Lewis structure, we're going to have geometry around each of the central atoms. And in this case, there are 3, right? There's this carbon, which has 4 bonding regions, and that's our tetrahedral geometry. There's this carbon here, which has 3 bonding regions, no lone pairs, and therefore is trigonal planar. Remember that whether it's a double bond or a single bond doesn't matter. It's still one bonded domain. And finally, we have this oxygen here, 2 bonds, 2 lone pairs, similar to water, and it's going to have a bent structure with 4 domains around it, but 2 are non-bonding, only 2 are bonding. That gives us a bent structure. All right, give this one a try now as well. We have 2 Lewis structures that you should first draw, and then determine what the molecular geometry of those structures are, remembering that we want to look at our central atom, and it's going to be based on the bonded and non-bonded electrons. So go ahead and pause the video, try this one, and we'll discuss. All right, hopefully you're able to come up with an answer, right? So we have CH2Cl2 and H2CO. So for the top, which is our dichloromethane, we have a tetrahedral geometry, right? 4 bonded zones, no lone pairs, and therefore it is going to be tetrahedral, right? For our second example, this is formaldehyde. We see that we're going to need a double bond between the oxygen and the carbon in order to fulfill our octet rules, and therefore what we're going to have is 3 bonded zones, no lone pairs, and it will have a trigonal planar shape. So this connection between the Lewis structure and the geometry is again very, very important, because what we're going to see is that this geometry is going to determine something called the polarity, which is going to determine many physical properties and explains why water and carbon dioxide are so different, right? Water liquid at room temperature, carbon dioxide gaseous at room temperature, and this really determines a lot of the chemistry that they engage in as well. So polar molecules, right? Recall that we have this value called electronegativity that says how much does each atom want to have the electrons within a covalent bond. And so when we have HCl, chlorine is more electronegative than hydrogen. And therefore we have a polar bond, and we have a bond dipole that shows that the electrons want to drift towards chlorine compared to hydrogen. Now, this is a pretty straightforward example because there is only one bond, but in the more complicated examples we've seen, what we're going to need to do is add up the bond dipoles to get what we call a net dipole. And in this case, right, the bond dipole is the net dipole, and so we say, well, it has a non-zero net dipole. Total dipole of 0, which we'll see in a second, means nonpolar. And in this case, we do have a net dipole, and so we have a polar molecule, which is HCl here, hydrochloric acid. What about the case of H2O versus CO2, right? Well, we see that the carbon-oxygen double bond and the OH bond are both polar, but does this mean that these molecules are both polar? Well, not exactly, right? Because we see here that CO2 has a linear geometry, and the bond dipoles are going to cancel. However, water has a bent geometry, and the bond dipoles will not cancel, and we can see this in the image below, right? We know that carbon and oxygen here are going to, carbon's always carbon, oxygen's always oxygen. So the carbon-oxygen bond dipole on the right is going to be equivalent to the bond dipole on the left. And we know that it's a linear geometry. So those bond dipoles will be pulling in equal and opposite directions. Therefore, the overall dipole on carbon dioxide is going to be equal to 0. In the case of water, we do have the same case with the oxygen-hydrogen dipoles. They're both equivalent, the bond dipoles. However, because of the bent structure of water, we're going to have those two arrows add up. They're going to cancel out in their kind of inward directions, but the upward direction will add, and we're going to have an overall dipole for water. And as a result, this shows that carbon dioxide is nonpolar while water is polar. And again, the strength of this separation will depend on the electronegativity difference between these different atoms. It's really just vector addition, adding up these arrows in three-dimensional space. But this is really, I think, a very clear-cut case that shows that molecular geometry is going to affect the overall dipole. And keep in mind, right, that if we're going to have a nonpolar molecule, everything's going to cancel. And this really does happen quite a bit, right? If you go back to our CH4 example, that one, everything will cancel as well. So only in cases where we do have some basically asymmetry will we end up having a polar molecule. In the next video, we're going to talk more about this polarity and how it leads, again, to what we call intermolecular forces, which determines whether something is, solid, liquid, or gas at room temperature, and again is really all about those physical properties that we discussed. So thank you for watching, and I'll see you in the next one.